Mecanum drive is the key to truly agile robot movement. Sideways, diagonally, any direction you need. Stick with me, and by the end of this video, you'll have a Python-controlled Mecanum robot that can strafe and glide with ease. Mecanum drive isn't just a neat trick. It's a big step up for your robotics projects. I'm Brogan Pratt. With over a decade as a robotics and design educator, I've guided many students through this exact process. Today, I'm going to run you through the entire setup. We'll start with wiring your robot, then we'll get straight into the Python code, line by line, to give your robot that full omnidirectional control. Let's go jump in. All right, so let's talk about what kind of electronics we're going to use. For our microcontroller, I'm using a Metro M0 Express. I've also used Metro M4 Expresses in the past. This is a great little board because it's the same form factor as Arduino, but it allows you to program in Python. Our motor controller is the RoboClaw 2x30 amp. A 2x15 amp would also work. Even a 7 amp would work. Just depends how big your robot is. In this case, I'm using 2x30 amps because I'm pumping through a lot of power. In terms of the mode settings in this, it's going to be mode 1, option 4. And you can set those using these specific buttons here. I have 2 of them because it's only able to control 2 specific motors. You've got power in, you have motor 1 and motor 2. I'm going to be using a 12-volt battery pack as my main battery source for the DC motors. And then I'm going to be using a 9-volt battery pack for controlling the microcontroller itself. As far as all these wires and things go to be able to connect things, I've got the bullet connectors that connect to DC motors. I've gone ahead and put on a few ring terminals here, and that makes it just a lot more secure when we're connecting it to our motor controller. For the controller, I'm using the FSi6 controller here by FlySki. This is typically used for RC planes, but it works wonderful for setting this up. So for our DC motors here, I've gone ahead and ran the cables up through one of these center wires here. Be careful as you're running through this. Aluminum channel can be quite sharp, and you don't want to actually cut your wires as you're pulling it through. Putting some sort of plastic collar or protector around here is likely a good idea. GoBuilder has these little plastic collars here, but you can also 3D print them. So I'm going to go ahead and feed these through so that we end up with some nice protection for our cables. Because you definitely don't want to be scratching your cables to the point where you end up shorting out your motors because they have cut the edges there. There we go. Nice protection. Let's do that on the other side. With that all set up, next thing is our battery. Now with a Mecanum drive, you really need to make sure that your center of mass is directly in the center of the robot. If you have mass on specific weights or at specific points, you're actually going to end up strafing in a bad position or poor position. So you want to be as symmetrical this way and this way as you can. So I've got this little battery mount here that I'm going to be mounting on this side that allow us to get that 12-volt battery in like so. Now I'm just going to use some of our old friends, the cable ties or zap straps here to hold this in. Because trying to get a part through here is a gigantic pain. So using some cable ties is going to make our life a lot easier. Let's go ahead and loop that around. Give it a little pull as we twist it in there. And then same thing on the bottom. You might find that with the cable ties, if you take the end and you bend it like so, it allows you to get around some of those corners a little bit easier. Okay, our battery mount is all squared away. We can grab some little flush cutters and snip off the end of those cable ties. And we can put our battery in like so. Then I'm also going to use a cable tie through the end here to stop this from coming out. And actually, instead of cable tie, I might use a piece of Velcro. Cable tie and Velcro are some of my greatest friends. They are awesome for cable management with your robotics projects. This will stop our battery from sliding out of our holder as we go around. And then Velcro makes it super easy to take this thing out later. Beautiful. Okay. So with our battery in there secure, let's go ahead and put on our motor controllers next. Motor controllers, I'm going to go ahead and face. I want the part where I'm actually be connecting our motors in like so. And I'm going to, again, just use a couple zip ties here. I'm going to use my little folding trick so I can easier Get that through. Push that through on both sides and line up my hole. And we'll, again, do that little folding trick. Get us through. Zip ties and cable ties. Velcro is a fantastic temporary solution for holding things together. And as much as you might think it is a little bit jank, perhaps, as opposed to using bolts, if it's good enough for holding things down on the European Space Station, it's good enough for your robotics project. Go ahead and clip those off. Now let's go ahead and put on our main control board. I'm going to put the main control board at the back here. Again, I'm going to be connecting this down with some cable ties. I love that little fold in the end of cable ties trick. And with my MicroController here, I've got a little mount that allows me to attach a breadboard to it. I find it super handy. Now for our main battery, we need to add in our switch here. So what I've done with my switch is I've simply just pulled out the positive lead, and I get a male Tamiya out to two XT male 30 connectors. So we're going to mount this in a place that would be nice and safe on our robot so we can easily access this at all times. I'm going to choose the back over here like so. You always need to be able to access your power button in the case of an emergency. So we're going to make it nice and easy to reach. Also, a big, bright red flashing button makes that fairly easy to know. We'll put in a second cable tie here. And maybe push up from the bottom. I'm going to fold that around, do a little double fold. Get that up and around so it almost makes like a J. So a little easier to get it up and through that main mounting hole. There we go. Oh. Spoke too soon. Not quite beautiful. Almost beautiful. There we go. With your battery supplies, you almost always want to have some sort of switched supply. Okay. And we're on there pretty good. We can go ahead and connect our battery terminal up now. Make sure our switch is off for now. And then let's go ahead and connect these to our RoboClaw controller. Now the RoboClaw controller here, I've got these little pinout points where I simply just have ring controllers out to an XT30. And that just makes it easy so that things are always connected strong. Now with these little screw terminals, I'm going to use a magnetizer. Allows me just to pull a screwdriver through. I can just lay it in, pull it back through. And it creates a temporary magnetic field so that I can have my parts not fall off the end here. So let's go ahead and screw on our XT30 connections. For our battery. And it looks like I might actually need to get an XT30 extension cable for one of these. Make sure you definitely do negative to negative and positive to positive on this. Otherwise, you'll end up blowing your motor controller. There we go. Let's go ahead and plug one in on this side. And then I'm going to have to go get an extension cable for that. Now, if you don't have a switch that already does things off on a Y, you can use one of these Y terminals, and I'm actually going to use this as my extension cable for now. Not best practice, should be using a different extension cable so things don't come up, but because technically these are two live terminals now, so I'm just going to make sure that I Velcro these out into a safe location so that I don't have to worry about where it is that they're going. I think I'm also going to add one more zip tie to this power switch because I'm not putting this power switch in with some bolts. I'm going to make it a little bit more secure, like so. Beautiful. Let's go ahead and connect up our motors. Now with our motors, I've done the same thing. I've done those ring terminals over to our bare bullet connectors. You don't need to do this. You could technically just cut off these bullet connectors and screw them directly onto your terminal. I'm not a big fan of doing that though, because these ring terminals, especially with these robotics projects, I like to take them apart and rework them again. Makes life a lot easier. Now on your RoboClaw controller, you have an A and a B section. You have M1A, M2B, and then B and A, and they are reversed on each other. So B is the inside on both, and A is the outside on both. Again, with a DC motor, it doesn't actually matter which side you run things to. What matters more is on a DC motor, you can actually have these things. When you reverse the player, it just reverses the direction of the motor. So for my ease, I always like to say B is ground and A is positive. So I'm going to screw on our screw terminals, assuming that logic. Grab another one of those. Watch that you're not grabbing your cables up and under on things so that you are always making sure your cable management is nice and clean every time. You don't want to try to have these things be gigantic jumbles of wires. So don't just put things wherever it is you're feeling. Notice how I'm not connected through my battery. Let's go ahead and spin this around. We'll do the other side now. Again, B is going to be our ground terminal for now. And then our last cable here, underneath my power cable. I'm using M3 ring terminals. Oh, I'm a little bit cross-threaded there. There we go. I'm using M3 ring terminals because that is the size of the screw for my RoboClaw controller. There we go. Now that's all set up. Let's go ahead and actually wire up these DC motors. Now looking at our motor here, I'm going to make this motor control on the side control the right side of the robot, this side control the left side of the robot. Now, typically when you wire up a Mecanum drive, the right side is inversed, and you inverse it in hardware so that you can program everything using positive values in your code. It may seem a little bit confusing now, but it's going to make it a lot easier to program later. So on the left side of our robot, we're going to grab the front motor. What I like to do is I like to look down in the bottom and I give it a little wiggle. And when I give it a little wiggle, I can see which motor it is that I'm working on. And I'm going to connect this one to motor 1, which is going to be actually the closest. Is it the closest side? Yes. Motor 1 is the side closest to us. So I'm going to connect red to red and black to black. And on the other motor, I'm going to make sure I don't get myself all tangled up. I'm going to get to the motor 2, and I'm going to go red to red and black to black. Now on the opposite side, I'm going to do that in reverse. So I'm still going to give a little wiggle so I can see which motor it is that I'm grabbing. My front right motor is going to go to motor 1 still, which in this case is going to be the far one. But this time, we're going to inverse that polarity. So we're actually going to go red to black and black to red. And all that's going to do is that's going to reverse the direction of our motor, make it way easier to program. Do the same thing over on this side. Again, red to black and black to red. And let's go ahead and cable manage these out of the way. Velcro is one of my favorite tools for cable management. We'll just go ahead and loop these all up into each other. Grab a strip of Velcro, and we'll just run it around itself. The reason I like Velcro is it's super temporary. Cable ties are not really fast for getting things done, redone, and undone, but Velcro makes life so much easier. Again, just like cable ties, while you might not think that Velcro is an intense tool to use, if it's good enough for the International Space Station to hold astronauts while they sleep, it is good enough to hold your motor controllers in, provided you're actually using a decent strip of Velcro. Alrighty, those are all up there, looking nice, looking a little more pretty now. Now let's go ahead and actually do our wiring for everything else. So let's do the wiring of our FlySki controller first. Now in our FlySki controller, this setup, you have your channel 1 all the way up through channel 6, and the top one is your battery and voltage. On this controller, you have an iBus, and then you have your PWM outputs. We're going to be using the PWM side. And I've made up a quick little chassis harness here that allows me to pull out channels 1, 2, 3, 4, 5, 6, and then output them over to the other side. So with this one, I can actually go ahead and wire this in nice. So now I have my signals for our power on this side, and then we have our 5 volt and our ground for our main motor controller. This one's also Technic compatible so that I can push this on like so and not have to worry about things going flying away. Actually, I'm going to go ahead and wire this up over here. Beautiful. We're ready to rock. Now I can go ahead and do our, for me, orange and white is 5 volt and ground. So I'm going to connect this to 5 volt and ground, our motor controller. And then I'm going to, for me, brown and brown-white are channels 1 and 2 respectively. So I'm going to go ahead and connect these up to channels 13 through 10 on my connector here. And then I also have a channel 4 that I'm connecting to digital 9. I'm not going to connect channel 3 today because I'm not using it in this project. Now let's go ahead and connect our RoboClaw controller on. Now for our RoboClaw controller, we're only going to use 3 ports here. At the start, down here by our serial ports, we have our S1, S2, and then ground is going to be this far side. So I'm going to go ahead and connect S1 and S2 and do the same thing on this side, S1 and S2, and a ground so we can get back to a common ground over here. So let's grab some jumper cables. Now this motor controller, remember this one's controlling the left side, and motor 1 is the front left. So I'm going to go ahead and do servo 1 over to digital 0 on our microcontroller. Then I'm going to connect servo 2 or S2 over to digital 1 for our rear right. Oh, actually, so I'm going to go digital 2 on this one for the rear left because I'm going to use the front right motor for that one. And then we need to get a ground. So I'm going to go ahead and grab a ground. At any point along this ground rail, this far right one is fine. We'll connect it to a ground on our Metro board. I'll connect to the ground up here. We're going to have to actually cable manage that out of the way. Otherwise, we're going to run into those all day. So let's go ahead and just tie up these points for our battery so that it doesn't get in the way, like so. There we are. That's the exact same thing on the other side. Let's grab that S1 again. We're going to connect this one to digital 1 because it's going to be our front right. And then S2 over to digital 3 for our rear right. And then we also need a ground again on this one. So we just grab a ground pin. Doesn't matter which one you choose. Coming over to a common ground on our Metro board. Now, last thing I'm going to say is having your radio receiver here directly by a battery and directly by a motor controller, it can produce a lot of electrical noise. I have not found so far with this project that does meaningfully impact this. But if you do find it's meaningfully impacting it, move your radio receiver further away from your motor controllers because your motor controllers are quite noisy with sending out signals. Last thing we need to do is do up our battery, our 9-volt battery. Again, I'm going to use our old friend Velcro here just to hold on. Oh, that Velcro is too short. Let's grab a longer strip here. I'm going to go ahead and hold on our battery pack so that things don't go flying away on us. So we got our 9-volt battery pack here. We can go ahead and connect that to our DC controller. And we're now all wired up. So let's head on over to the computer And let's start programming this. So over at our coding program, let's take a look at how we're going to break down our steps for today. So our programming steps today are, one, we're going to have to set up our RC controller so we can have our inputs. Two, we're going to set up our DC motor controllers. We're going to have to set up, or we're going to have to create a helper function that converts milliseconds to a duty cycle pulses. We need to do that because our motor controller assumes you have a 400 milliseconds of range, but we need to convert those into duty cycle pulses because that's actually how we're going to control our motors. After that, we need to create a helper function that normalizes the joystick input. And then finally, we're going to create a drive function that takes our normalized inputs and outputs Mecanum to drive motor commands. So let's start with that first part where we need to actually set up our RC controller. First thing we do, as usual, is we're going to import time. We're going to import board. And we're also going to say from RC, import RC. So this is a class you can find in the library down below that allows us to use the FlySki FS1 or i6 controller with CircuitPython or Python. And we're going to create the RC object. And this was simply going to be RC equals RC. And then here's where we create all of our different channels. So we're going to be reading channel 1, and this is going to be board.D9 in my case. So actually, sorry, this is D10 in my case. Channel 2 is equal to board.D11. Channel 3 is equal to none because we're not reading channel 3. And channel 4 is equal to board.D9 in my case. Channel 5 is equal to none. And channel 6 is equal to none as well. Oops, not equals. So that is our RC object initialized. If you'd like to have more switches, you could go ahead and actually import these channels. But so in this case, we're not actually going to be doing that. Then let's actually read our channels. And this is pretty easy. So we'll say while true, we're going to say our throttle is equal to rc.read_channel. And our throttle is the y-axis on our right joystick, which is channel 1. Our strafe is equal to rc.read_channel. And our strafe is actually going to be channel 2. Then finally is our rotate, and that is equal to rc.read_channel, and this is going to be channel 4. Now at the very end of our loop, because we're reading on that RC, on the specific controller we're using, we are reading PWM cycles, and we need to stay within a PWM loop. So I'm actually going to put in a time.sleep for 0.02, and this keeps us in cycle with the PWM of the RC controller. We've now set up our RC controller. We're ready to rock. Let's go on to the second step, which is setting up our DC motors. Now for our DC motors, we need to import another library. We're going to import PWM IO, or pulse width modulation in out. And let's actually create these 4 different objects. So we're going to create 4 motors. We're going to say motor_front left is equal to PWM IO.PWM out. And this one is going to be, our front left is board.D0, and it's got a frequency of 50. We're going to create this for our front right, our rear left, and our rear right. And thankfully, using Copilot, it's actually pretty smart here. These are all actually correct. So we've got our front left, front right, rear left, and rear right, all to our respective motors. Now, before we continue on, we need to set up some default ranges so we know where we are actually at. Using the RoboController over serial output, the stop milliseconds is equal to a 1.5 millisecond pulse. So if you send a 1.5 millisecond pulse to a motor, it's going to stop it. Our max milliseconds speed is going to be 1.9, and our min millisecond speed is equal to 1.1. So we actually have a 400 millisecond range, plus or minus, to control max power of the motors. You might want to check the documentation on your motor controller to make sure yours is the same, but for my motors, this is where things are going to be sitting at. So now we've got our default setup. It's time to go ahead and convert those millisecond pulse commands into a duty cycle. We're going to use a helper function to do this because the duty cycle is going to be a full 16-bit analog range, which means we've got 65,535 values to work through, which is why we're using these millisecond cycles as opposed to having to type it in. So we're going to create a new function, and we're going to say millisecond to duty cycle. And for this, we're just going to assume a frequency of 50 because we've already done so. So we're going to say it's going to take millisecond as an argument. It's also going to take frequency as 50. First thing I'm going to do is I'm going to take a period of milliseconds is going to be equal to 1.0 divided by our frequency multiplied by 1,000. And then to actually get our duty cycle is equal to an integer division of our milliseconds divided by our period milliseconds divided by 65,535.0. So that gets us our duty cycle number. Now we need to make sure that the duty cycle that we send is in between the ranges of 0 and 65,535. So the last thing we're going to do is we're going to do a quick clamping helper function. So we are going to return the minimum of 65,535 and the maximum of 0 and our duty cycle. So this just clamps the duty cycle from 0 to 65,535. Effectively, how it does that is first it's going to calculate the maximum value between 0 and the duty cycle. It's possible that our duty cycle gets calculated as a negative number, in which case the maximum we should take is a 0. And then it's going to take the minimum number between the absolute maximum value and whatever the value was here. So it's possible that this duty cycle ended up being 70,000. Then it's going to take that minimum number between those two. So it'll always pull between 0 and 65,535. So next is one of our really important helper functions. We're just going to create a stop all function. It's really useful in robotics to have something you can use as sort of your red button if something goes wrong. So let's create that. So we're just going to find stop all motors. It's not going to take anything. And whenever we call this, we're just going to stop everything. So I'm going to say motor underscore front left dot duty cycle is equal to our milliseconds to duty cycle function, and then stop milliseconds. We're going to call that down for all of our motors, for our front left, our front right, our rear left, and our rear right. So whenever we call that stop all motors, it's going to send that millisecond to duty cycle helper function with our stop milliseconds, which of course is 1.5. So this should stop all of our motors. Important thing about this roboclock controller is whenever you send a command to it, the motors will continue to run. So if you don't send a stop command, they won't actually stop. So this is a really useful function. At this point, we've set up our RC controller, we set up our DC motor controllers, and created the help for our function that helps us convert those milliseconds over that duty cycle. Next, let's go ahead and create that helper function that normalizes that joystick input. The reason we have to do this is with the RC controller that I'm using, it expects a range of 0 to 100 from the joystick. However, in order to control Mecanum wheels, Mecanum kinematics expects between negative 1.0 all the way up to 1.0. So we need to be able to normalize that input value from 0 all the way up, or from negative 1 all the way up to 1. So let's go ahead and create that function. So I'm going to say define normalize input, and we're going to take a value as our parameter. Now, the first thing we need to do is we need to set up our dead zone. And what a dead zone is you'll probably find that with some controllers, that center joystick doesn't really bring itself back all the way to center. We would expect that 50 is the center, but sometimes when it releases back, it's not always back to that center. So we're actually going to say dead zone min is going to be equal to 45, and the dead zone max is going to be equal to 55. And then we'll check if our value is within those dead zone mins. Before that, we're actually going to check if the value is equal to none. We're simply going to return 0. So if our value is equal to none, we're going to return 0. What this does is if we pass in a none value, and that will get exported, or that will get returned with that RC controller. It returns none if it gets an invalid reading. So this allows us just to stop the controller. Because 0.0 is going to end up actually creating a stop for us because that's our mid value. Then we're going to check if our value is inside that dead zone. So we're going to say if the dead zone min is less than or equal to our value, and our value is less than or equal to our dead zone max, so our value is in between our dead zone, we're actually going to go ahead and return 0 again. So a lot of stopping functions, but again, robots are all about safety. So now that we know that our value is going to be in that dead zone, let's actually see what happens if we are pulling back on that controller or below our dead zone value. So we're going to say elif the value is less than the dead zone's minimum value. We're going to return our value minus our dead zone min divided by our dead zone min. So effectively what this is going to do is it's going to turn whatever that value between 0 and 44 is into a decimal number between negative 1.0 and 0.0. Then we're going to say elif our value is greater than our dead zone max. We're going to return our value minus our dead zone max divided by, this time it's going to be 100 minus our dead zone max. And this is going to do the exact same thing. It's simply going to return above 55 and it's going to convert that 1.0. So at this point, we've now got all of our helper functions set up. And now we can actually finally go ahead and create that drive function that's going to go ahead and move our Mecanum wheels. So we're going to go ahead and say define drive. And our drive is going to take 3 parameters. We need to take our throttle speed. We need to take our strafe speed. And we need to take our rotate speed. And so we're actually going to one more. We're also going to add in an input scale. And what an input scale does is it allows us to effectively change the sensitivity of those joysticks. So if you find, rather than having to change the joysticks themselves, you can change the 0.5. If you make it greater up to 1.0, it'll make it so you get an absolute transfer. If you bring it down, it makes it so that your joystick command doesn't go as fast. It'll make things a little bit less jumpy. It's nice to have a bit of proportional control in here. This is future Brogan coming in to edit this. I realized I made a mistake there. It should be strafe, and now my whole function will actually work. I had accidentally wrote this as input scale in parentheses 0.5. It's actually input scale equals 0.5. Didn't catch that until I went through back and edited it. So first thing we're going to do is we're going to normalize all those inputs. So we're going to normalize our forward input, which is going to be our throttle speed, but we're going to put it inside our normalize input value. So we're going to say normalize input, and we're going to normalize our throttle speed input. We'll do the same thing for our strafe and our rotation. So I'm going to say that strafe is equal to, again, normalize input, but our strafe speed, and then rotate is equal to that normalize input, but our rotate speed. Then we're going to check if those values that we sent are within that dead zone. So we're going to say if our forward is equal to 0, and our strafe is equal to 0, and our rotate is equal to 0, we're just going to call stop all motors and then return a null value. This is, again, another one of those safety functions. If your joystick happens to be in the direct center, you're not touching anything. When you're calling drive, of course, nothing should be moving. If those values happen to be outside of drive, let's go ahead and actually send those out. So we're going to multiply in our scale so that we can scale down some of that sensitivity. So we're going to say forward is equal to forward times input scale. Same thing for strafe and same thing for rotate. Now let's actually do our Mecanum kinematic equations here. So in order to do those equations themselves, we're going to send power to each individual motor. So we're going to say motor underscore front left power is equal to forward plus strafe plus rotate. Our motor underscore front right underscore power is equal to forward minus strafe minus rotate. And then our motor underscore rear left power is equal to forward minus strafe plus rotate. And then our motor underscore rear power is equal to forward plus strafe minus rotate. And I actually have a spelling mistake here. There we go. If you want a deeper explanation into how these kinematics actually work, I've got a video in the description down below about how these mathematics actually transfer those forces into directional movement for your Mecanum drive. But effectively, this is the quick equation that allows you to move everything out. Next, it's time for us to make sure that we clamp that power between -1 and 1.0. What you'll find is that it's entirely possible that you have a forward and a strafe value of 1 and a rotate of 0, and it's not possible to have a motor command that is greater than 1. The problem with that is you cannot send 200% power to one motor and 100% power to another because it'll only accept 100%. So we're actually going to scale everything down a little bit so that it clamps it between. And then if one of the motors is at 200%, one of the motors is at 100%, we're actually going to call the other motor at 100% and the other motor at 50% so that the ratio stays the same for what it is that we would expect the output to be. If we don't do that and we would want to go forward and diagonal, we'll actually end up not moving the direction that we want. So the first thing we need to find is we need to find which motor is currently the strongest. And the current max power is equal to the maximum of our absolute value of our motor front left power, then the absolute value of our motor front right power, absolute value of motor rear left power, and rear right power. We grab that absolute value because it's possible we have a negative 2.0, so it basically removes that negative and says whatever our current value is. Then Copilot is smart enough here that if our maximum power is greater than 1 or higher than that, we're going to scale all the motors down based on whichever power was the highest. So it's entirely possible that one of them is actually sending 3.0 value. So then it would scale everything down by 1/3. Now, the last thing we need to do is actually command the motors to move. So we're actually going to move the motors and convert to milliseconds. So we're going to grab our motor underscore front left dot duty underscore cycle is equal to, so we're going to actually send out that duty cycle in something that is between 1.1 and 1.9. We're actually going to take our stop milliseconds value. We're going to add in that motor front left power. And we're going to multiply that by 0.4 because 0.4 is that range in between. And that's going to end up giving us that value between 1.1 and 1.9. We're going to go ahead and do the same thing for the front right, the rear left, and the rear right value. So now we've got our drive function set up. Let's actually go ahead and control these motors in the very end. Add inside of a while true loop, after we've read all the values for our controller, we're going to go ahead and simply grab drive, and we're going to call it with throttle, strafe, and rotate. And that's it. That's how we actually program something up in Mecanum Drive. Let's go take a look and see at how this actually works around. So a brief overview of how everything works again. We set up our RC controller. Again, that's for my specific setup. You might be using a Bluetooth controller, whatever it has. We set up our DC motor controllers. We create that helper function that converts our milliseconds to duty cycles, create that helper function that normalizes joystick input, then creates that drive function, actually takes those normalized inputs and outputs it into those Mecanum Drive motor commands. We import the required libraries, create our RC object, go ahead and create our DC motors. For ours, my specific commands are stop of 1.5 for the maximum minimum of 400 milliseconds either way. We have that helper function that converts our milliseconds into a 16-bit cycle. And then we also have our stop motor function. We've got our normalizing value that allows us to keep track of dead zones. If you find this dead zone is too great or too little, you want things a little more sensitive, you can change those dead zone values. This is where we actually drive. We take in our throttle speed, our strafe speed, and our rotate speed. We check if those are all 0, we stop our motors. Otherwise, we multiply by our input scale, and then we do our actual Mecanum mechanics before we check. And if anything's greater than 1, we ratio everything down before finally actually sending those motors out. So I hope you found that a useful case in converting Mecanum Drive into Python controllers. If you got any questions, let me know in the comments below. And if you have ideas for future projects or other things you need help with, shoot a comment and maybe I'll make a video on it in the future. So I hope you had some fun and best of luck with your next robotics project.